Hello everyone, I am Anusha BM from Shankar College of Engineering, Bangalore from ECE Department, Section Astus, Semester 3, USN 1VE23EC009, Course Electronics Principles and Circuits, Course code BEC 303. Now I am going to give small presentation about emitter feedback bias, collector feedback bias, and collector and emitter feedback bias. Introduction to feedback bias methods. Feedback bias methods are crucial in designing stable transistor amplifiers. They help to maintain the operating point despite variations in temperature and transistor characteristics. Understanding these methods is essential for effective circuit designs. What is emitter feedback bias? Emitter feedback bias is a technique used to stabilize the biasing of a transistor. It employs a transistor connected to the emitter to provide feedback. This feedback helps in controlling to the base current and stability that operating point. Circuit diagram for emitter feedback bias. The emitter feedback bias circuit typically includes a resistor to connect it from the emitter to the ground. The base is connected to the voltage divider network for biasing. The configurations allows for negative feedback enhancing stability. Advantages of emitter feedback bias. It provides good thermal stability due to negative feedback. The circuit can handle variations in transistor beta current gain effectively. Emitter feedback bias is a simple in a design and implementations. This is the emitter feedback characteristics too. Q point relationship. High B is equals to VCC minus VBE by RB plus HFE plus 1 into Harry. High CQ is equals to HFE into high B. High CEQ is equals to approximately VCC minus ICQ Harcy plus Harry. Disadvantages of emitter feedback bias. The output impedance may vary affecting signal quality. It may introduce a slight introduction in a voltage gain. The design may require precise component values for optimal performance. Emitter feedback characteristics. What is collector feedback bias? Collector feedback bias is another method used to stabilize transistor operation. A feedback resistor connects the collector to the base of the transistor. This configuration enhances the stability of the operating point through negative feedback. DC bias with a collector voltage feedback. Another way to improve the stability of a base circuit is added or feedback path from the collector base. Circuit diagram for collector feedback bias. The collector feedback bias circuit features a resistor from the collector to the base. The emitter is typically connected to the ground for a through an emitter. This setup allows for the feedback to adjust the base current in response to collector voltage changes. Advantages of collector feedback bias. Collector feedback bias provide excellent stability against temperature variations. It is partially effectively in high frequency applications. The design is simple and requires fewer components than some other biasing methods. Disadvantages of collector feedback bias. It can result in a lower signal gain compared to other biasing techniques. The input impedance may be affected due to the feedback. Circuit may be less stable for applications requiring high output impedance. Collector feedback bias. High B is equals to VCC minus VBE, RB plus B plus 1 into RC. VC is equals to VCC minus IE Hari. What is collector emitter feedback bias? The collector and emitter feedback bias combines elements from both feedback methods. It uses a feedback from both the collector and emitter to stabilize the base point. This technique enhances the stability and performance of the transistor amplifier. Emitter feedback bias. If an emitter resistor is added to the base circuit, we get an emitter feedback base. Help make base bias more predictable with the negative feedback which negates any attempted rate change in collector current with an opposing change in base voltage. If the collector current tries to increase, the emitter voltage increase causing an increase in base voltage due to VB is equals to VE plus VBE. This increase in base voltage reduces the voltage across RB, thus reducing the base current and keeping the collector current from increasing. Circuit diagram of collector and emitter feedback bias. In this configuration, the resistor had connected both the collector and emitter to the base. The dual feedback setup allows the tighter control of the biasing condition. This circuit design ensures the robust performance across range of operating. Advantages of collector and emitter feedback bias. It offers a superior thermal stability compared to using either method alone. The circuit can maintain a constant gain over a wide frequency range. This biasing technique is a versatile and can be used in various applications. Disadvantages of collector and emitter feedback bias. The complexity of a circuit design may increase due to additional components. Fine tuning is a feedback resistor may be necessary for optimal performance. The overall gain can still be lower than that achieved with other configurations. Partially applications of feedback bias method. The biasing techniques are widely used in Hawaii amplifiers. They are also employed in RF amplifiers to ensure stable performance. Feedback bias methods are essential in creating reliable and efficient electronic circuit. Summary of emitter feedback bias. Emitter feedback bias is effectively tough for thermal stability and easy to design. It reduces the sensitivity of variations in components parameters. This method is commonly used in low to moderate frequency applications. Summary of collector feedback bias. Collector feedback bias enhances the stability and is stable for high frequency circuits. It offers simplicity in a circuit design with fewer components. However, it may compare the gain curtain applications. Summary of collector and emitter feedback bias. This approach combines the benefits of both previous methods and enhances stability. It is effective in maintaining constant performance across various conditions, stable for a wide range of electronic applications. It balances performance with design and complexity. Thank you.